Hello, everyone. Today, we will be covering Chapter 6, Section 3, Bitcoin Blockchain. The data structure of the Bitcoin blockchain consists of blocks containing transaction information, which are linked sequentially in chronological order. Its core client utilizes Google's LevelDB database to store blockchain metadata. Each block header undergoes SHA 256 encryption hashing to generate a hash value. Now, the block identifier includes the block hash. This block header is a digital fingerprint obtained by applying the SHA 256 hash function twice, with a fingerprint length of 32 bytes. The block hash uniquely identifies a block, while the block height represents its position in the blockchain. The first block has a height of 0, with each subsequent block linking to the previous one. Each block is positioned one step higher. The Genesis block, as mentioned earlier, was created by Satoshi Nakamoto in January 2009. It serves as the starting point of the entire blockchain. As blocks are sequentially connected, they form the longest main chain from the Genesis block to the latest block, preserving the complete history of blockchain data. Any data can be traced back through this chain structure. This is why blockchain is considered tamper-proof and traceable. Its characteristics lie in this structure. All blocks are interlinked step by step along the timeline, forming an unbreakable chain that no one can alter. Now, let's introduce an important concept in blockchain, the Merkle tree. The Merkle tree is used for efficiently summarizing and verifying the existence and integrity of blockchain data. It consists of the transaction database, the root hash of the block header, and all branches connecting the underlying block data to the root hash. Since the Merkle tree is a binary tree, it requires an even number of leaf nodes. If there is an odd number of transactions to be summarized, the last transaction will be duplicated to form an even number of leaf nodes. Such a structure with an even number of leaf nodes is called a balanced tree. Now, let's move on to timestamps. Bitcoin blockchain technology requires the node obtaining accounting rights to add a timestamp to the block header, indicating the time of block data entry. Timestamps serve as strong proof of the existence of block data, contributing to the formation of an immutable and forgery-resistant blockchain database. Next, let's discuss Bitcoin's distributed consensus process. The proof-of-work consensus mechanism seamlessly integrates Bitcoin's currency issuance, transaction payments, and validation functions, ensuring system security and decentralization through computational power competition. Each full node independently verifies every transaction and broadcasts it to the entire network. By completing the proof-of-work algorithm's computations and verification, mining nodes package transaction records into blocks and broadcast them across the network. Each node independently validates new blocks and links them to its locally maintained blockchain. Under the proof-of-work mechanism, the blockchain with the highest cumulative work is selected. Now let's talk about blockchain forks. Blockchain forks essentially arise from inconsistencies between nodes regarding the blockchain state. All nodes always choose the blockchain with the highest cumulative proof of work, meaning the longest or most difficult chain as the main chain. As a result, the entire Bitcoin network ultimately converges to a consistent state. Bitcoin consensus attacks can be categorized into denial-of-service attacks and 51% attacks. The denial-of-service attack, also known as a dust attack, involves flooding the network with numerous low-value, low-fee spam transactions to congest the network and deny service to specific Bitcoin addresses. An attacker controlling the majority of the system's computational power can easily ignore a specific transaction. The 51% attack, also called the double spending attack, occurs when the same Bitcoin is spent on two different transactions. There is also the selfish mining attack, where a miner with significant computational power withholds newly mined blocks instead of broadcasting them, continuing to mine privately. Once their private chain surpasses the public ledger in length, they broadcast all withheld blocks at once. Another attack is the difficulty bomb attack, where an attacker with massive computational power suddenly increases the mining rate, drastically shortening block generation time. This leads to a difficulty adjustment, significantly increasing mining difficulty in the next cycle. If the attacker then withdraws their computational power, the remaining miners face extreme difficulty, slowing block generation and causing network congestion, thereby achieving the attacker's goal. Lastly, there is the empty block attack, where miners do not include transactions in the block, except for the Coinbase transaction, which is the transaction provided by the miner. Alright, everyone, that concludes Chapter 6, Bitcoin Blockchain. Let's now review the content of this chapter and summarize the key points. In this chapter, we focus on understanding the concept, development history, and current state of Bitcoin. Additionally, we delve into Bitcoin's core concepts, with a particular emphasis on mastering the Bitcoin blockchain. Alright, that concludes this lesson. Thank you all.